Hi everyone. So in this video, we're going to learn some rules about logarithms that will allow us to rewrite different logarithmic expressions in different ways. So just like a lot of other things with logarithms, so because logarithmic functions are so closely tied with exponential functions, all of the rules that we're going to be discussing in this video about logarithms are very closely related to rules about exponents. So I want to start by reviewing some exponent rules. So these are different. These are not going to be the same exponent rules that we talked about in a previous video. These are ones we have not discussed yet. But I think most of you will have seen these in the past and probably just need a quick refresher. Okay, so the first one I want to talk about is if you have two numbers with the same base, both being raised to a power. So how can you rewrite a number to one power multiplied by that same number to another power? How can we rewrite this as just one number raised to one power? Well, we could basically take that base, leave it the same, and then add together the exponents. So why is it that you add them and not multiply? You know, I think a lot of people tend to get mixed up and maybe try to rewrite this as b to the m times n, and that would not be correct. So why is it that you add? Well, let's look at a simple example. So let's say, for example, that you have some number cubed times the same number squared. So how could you write this out kind of the long way? Well, b cubed is the same as b times b times b. And b squared is the same thing as b times b. And so if you're multiplying this number together, you know, all of these times, you're multiplying it together a total of 3 plus 2, which is 5 times. So you can rewrite it as b to the 5th power. So if you ever forget these rules with exponents, just do a really simple example and you should be able to see why the rules work the way that they do. Okay, so what about if instead of multiplying, you're dividing? So you have b to the m over b to the n. Well, then instead of adding the exponents, you're going to subtract them. So you're going to do m minus n. And so similarly, we can see this by doing a simple example. So let's say that we had b cubed over b squared. Well, that would be b times b times b over b times b. And so what we can see is that two of the b's are going to cancel out from the numerator, right? And so what are you left with in the numerator? Well, if you subtract 3 minus 2, that will tell you how many of your original base is left over. And so you'll get b to the 1st power, which is 3 minus 2. Okay, so last rule that we need to know here is that let's say now that we have a number being raised to a power, and then we're raising that whole thing to another power. So in this case, this is where you actually multiply the exponents together. And so why is it that you multiply in this situation versus adding when you are actually multiplying the two original expressions? So let's do another example. Let's do b cubed squared. So if you have b cubed squared, what would be a kind of longer way of writing that? Well, that would mean that you're doing b times b times b, right? That's b cubed. And then what does it mean to square something? It means you're multiplying it with itself, right? And so if you're multiplying b times b times b with itself, that means you're doing another b times b times b. And so all in all, here you have 3, and then you have another set of 3, and so you do 3 times 2, and you get b to the 6th. So the difference is that when you're multiplying, like in this first example, that's just kind of counting up extra sets, right? Here we have 3, here we have another 2. If you had, b to the 4th, you would have another 4. And so you just keep adding on these extra powers of b, versus in this situation, the power that you're raising the exponent to is really telling you how many sets of that number of b you're going to have, right? So here you have 3 sets, or here you have 3, and then you have another set of 3. If this was cubed, then you would have 3 sets of 3, which would be 9. So that's the reason that these exponent rules work the way they do. I want to do one quick example of just seeing like how you might encounter these kind of exponent rules. So typically you'll see these exponent rules in a situation where you're trying to simplify some kind of a kind of complicated expression. So let's say that you have the expression x squared y cubed divided by x to the fourth times y squared. Okay, so how can we use these exponent rules to simplify? Well, basically, we can start by, in the numerator, applying that the rule that we have, number 3, right? And so one rule that I didn't mention here, but that, that you should also know, is that if you're taking something like this and raising it to a power, well, that means that both parts are being raised to that power, right? Because this would be like x squared y times x squared y times x squared y. So both the x squared and the y are going to receive that third power. So this would look like in the numerator, so I'm just going to rewrite it like this for a moment, x squared cubed times y cubed divided by x to the fourth times y squared. Okay, so now we're going to be able to apply the rule number 3, right? Because now we have x squared cubed, and so that's going to be x to the 6th because we multiply. So now we have x to the 6th times y cubed divided by x to the 4th times y squared. And so now what we can do is use that subtraction rule. So x to the 6th over x to the 4th, well, that's going to be x squared. And then y cubed over y squared, that's going to be y to the first power, which is just y. So this is the kind of situation where you would use these exponent rules. Okay, so let's go check out some logarithm rules that we'll see are closely tied to these exponent rules. Okay, so we're going to fill out this kind of table where on the left we have the exponent rules that we discussed on the previous page. And then we'll see that for each of these exponent rules, there's a corresponding logarithm rule. Now, for some reason, we like to, when we're talking about rules about logarithms, those tend to be called laws of logarithms, whereas when we're talking about exponents, we usually call them rules. I don't know why, but I'm just going to stick with that because that's kind of the convention. Okay, so the way that I want to link together the exponent rules and logarithm rules is basically by what kind of operations are happening in each of them. So what I mean by that is if we look at this first exponent rule, we start out with multiplication, right? We're multiplying together two numbers. And then what happens when you multiply those two numbers together? What happens with the exponents? Well, the exponents end up getting added. And then for the next one, we start out with division, right? We're dividing two numbers. And then what happens with the exponents when we divide? Well, that turns into subtraction. And then finally, this last one, it's a little harder to describe what's going on here, but I guess I'll call it just an exponent, right? So you're taking a number and you're raising it to a power. And that raising it to a power, what that becomes in the exponents is it becomes multiplication. Okay, so the reason that I'm writing down these kind of general statements about different operations is because that's what I think will help you to remember the logarithm rules, because I think the exponent rules are easier to remember. So if you can kind of characterize them based on what I wrote down in the middle here, I think that might help you link them to the logarithm rules. Okay, so first logarithm rule. So all of these are going to be true for a log with any base. So I'm just going to write them as log base b, but it could be ln, it could be log base 2, it could be whatever logarithm. So if you're taking a logarithm of a product of two numbers, so I'm going to write that as x times y. So you can split this logarithm up and notice that there's multiplication is what's happening inside the logarithm. So based on what we see here, we should expect that somehow addition is going to emerge from this, and it does. So if you have a logarithm of a product, multiplication of two numbers, you can split that up as a logarithm of the first number plus a logarithm of the second number, where we're keeping the base the same. And by the way, I'm gonna, once we fill out the rest of this table, I'm going to kind of explain a little bit better where, why each of these logarithm rules is true and kind of show an example to demonstrate that they actually work. Okay, so similarly, this next one is supposed to be about going from division to subtraction. So let's say that now we're taking a logarithm of a quotient of two numbers being divided. So how is this going to break up into two logarithms? Well, we can break it up as log base b of x minus log base b of y. And then the last one is about going from an exponent to multiplication. So this is going to happen when you have log base b of x raised to a power. So let's just say to the n. So the way that you can write that is you can kind of bring this exponent outside of the logarithm, and it's going to be n times log base b of x. So I want to look at a couple of quick examples to just kind of convince you that these rules work. Hopefully this idea about exponent rules and logarithm rules, gets you feeling like this could be true, but I just want to show you a couple of examples to really demonstrate that these rules work. So for the first one, just to remind you, was the rule that said that if you're taking a logarithm of a product, that we can split it up as a logarithm of, we can split it up with addition, right? As a log of each of the two numbers that we were multiplying together. So how can we kind of test this out? Well, we can choose to use numbers that we already know what the answer is. So what I mean by that is, let's say that we wanted to find log base 2 of 32. So we could either find that kind of from scratch, right, just by figuring out what log base 2 of 32 is, or if we wanted to see whether this rule works, we could also rewrite this as log base 2 of 4 times 8, right, because 32 is 4 times 8. So let's start by just evaluating log base 2 of 32 so we know what we're going for as our answer. So log base 2 of 32 would be asking us what exponent do we need to raise 2 to in order to get 32? And so the answer would be 5, right? Because 2 times 2 is 4, times 2 is 8, times 2 is 16, times another 2, that's 5 total multiplications is 32. Okay, so let's check what we would get if we tried to use this rule instead. So if we did log base 2 of 4 plus log base 2 of 8, what would that give us? Well, log base 2 of 4 is saying what power do we raise 2 to get 4, and the answer would be 2. And then log base 2 of 8 is saying what power do we raise 2 to get 8, and the answer is 3. And so 2 plus 3 is 5. That agrees with what we already know the answer is. So we've seen that at least for this example, the rule works. Maybe just to give a little bit of insight into like why this works. So if you look at 32, 32 can be written as 2 to the 5th, right? And that's really the reason that 5 is our answer, because 32 is 2 to the 5th. Now down here, we can rewrite 32 as 2 squared times 2 cubed. And so what ends up happening here is that in these two pieces, we have 2 squared and we have 2 cubed. And so from those come out the 2 and the 3. And so why is there a power of 2 and a power of 3? Well, because 2 plus 3 is equal to 5 because of exponent rules, right? Like the whole reason that we can rewrite 32 as 4 times 8 is because 2 to the 5th is the same as 2 squared times 2 cubed. So hopefully you can kind of see like why that exponent rule about addition kind of can come out in the context of logarithms as well. Okay, so similarly, let's say we wanted to demonstrate a similar idea, but now with the subtraction rule. So if we have log base b of x over y, we learned that this should be equal to log base b of x minus log base b of y. Okay, so what would be an example that could work here? Let's use powers of 2 again, just because those are fairly easy to work with. Let's say we were trying to find log base 2 of 8. So how could we write 8 as a division problem? Well, 8 is the same thing as 32 over 4. Okay, so what is log base 2 of 8? Well, we know that that is equal to 3, right? Because 2 to the third is equal to 8. And so let's see what happens if we try to use the logarithm rule. So we would get log base 2 of 32 minus log base 2 of 4. And so what is log base 2 of 32? Well, we just talked about this one, right? It was 5. And what is log base 2 of 4? Well, that's 2. And 5 minus 2 is equal to 3, which matches with what we know the answer is supposed to be. So we can see that, at least with this example, it works. So again, why is it that that works? And like, why is this related to exponent rules? Well, because 8 can be written as 2 cubed, right? And so that's where the answer of 3 comes from. And then looking at how we rewrote 8, well, that could be written as 2 to the 5th over 2 squared, right? And we know that there's an exponent rule that when you're dividing, you subtract. So 2 to the 5th over 2 squared is the same as 2 cubed. And so that's why when we subtract, 5 minus 2, we end up with 3. So it's basically because the exponents are the numbers that are coming out when you do logarithms that you end up subtracting the logarithms in this case, or in this case, adding them. Okay, last example to verify this last rule. So the last rule was saying that if you have a logarithm of x raised to a power, that you can rewrite that as you bring down that power and you multiply it with the logarithm. Okay, so let's do an example for this one of, let's say we're trying to find log base 2 of 16. So we know that log base 2 of 16 is 4, right? Because 2 to the 4th power is equal to 16. So similarly to the other ones, if we want to test out this rule, we need to figure out a way to write 16 as some power, right? And so let's rewrite 16 as 4 squared. So according to this rule, how do we go about evaluating this? Well, we bring down the exponent. So this would be 2 times log base 2 of 4. And so what is log base 2 of 4? Well, that would be 2. And so we would get 2 times 2, and that is 4, which matches with what our original answer was. So again, why is this working? Well, because 16 can be written as 2 to the 4th power, right? That's why our answer was 4. Now, what about 4? Well, that is 2 squared. So you can think of 4 squared as being 2 squared squared, right? And this 2 times 2 matches with the 4. And so that's why when we go and do this rule, we have a 2 squared coming from this part. And so that's where the 2 comes from. I know there's a lot of 2's floating around in this problem, but that's where this 2 comes from, right? And then where does the first 2 come from? That comes from the fact that we were taking 2 squared and squaring it. Okay, so if you didn't totally follow all of this, by the way, that's okay. Really what you need to know are these 3 rules. So however you want to go about remembering them is fine. I just think it's worth trying to understand where they come from, but even just thinking about these facts, I think is enough to give you some insight into why these rules work. Okay, so for the remainder of the video, we're now going to be doing some examples kind of akin to this example here, right? So at the beginning of the video, we did an example where we started with an exponential function and we simplified it, or an exponential expression, and we simplified it. And now we're going to do the same thing with different logarithmic expressions. So we're going to use logarithm rules, or laws, to expand the following. So what I mean when I say expand is we're going to start with expressions that look like one single logarithm, and we're going to break them into pieces. And it might initially seem like we're making these things more complicated, but the pieces we're breaking them into will be simpler. So let's jump into some examples. So first example, let's look at log base 2 of 8 times x. So how can we break this down using logarithm rules? Well, we can use that first rule, right? We can rewrite this as log base 2 of 8 plus log base 2 of x. And so in this case, log base 2 of 8, well, that's actually a number, right? Log base 2 of 8 is 3. And so we can rewrite this as 3 plus log base 2 of x. So, you might look at this and say, well, I feel like that's more complicated than what we started with, right? Because our first thing was just one logarithm. Now this is like 2 pieces. The reason that being able to do this kind of thing is valuable is because when you get to calculus, you're going to be doing something called taking derivatives. And with derivatives, the more complicated a function is, the harder it is to take its derivative. And so one kind of general strategy for taking derivatives is to start with a more complicated function and find a way to break it down into simpler pieces. So it's kind of like when we were talking about function composition and we did those problems where you take one function and you kind of break it down using composition. Similar idea here. We're breaking functions down or breaking expressions down using log rules, and that would then give us, in the context of a calculus class, pieces that are easier to work with. Okay, let's do another example. Let's say we're doing log base 5 of x cubed times y to the 6th. So what we'll see in a lot of these examples is that we're going to be using multiple of those different logarithm rules, and I think the main challenge is just kind of figuring out what to do first. So in this case, we see that we have exponents on our variables, and so that tells us that we're going to eventually use that rule where we bring the powers down. But first, we need to split this up. So the reason we need to split it up using the multiplication to addition rule first is that you can only use this rule, this last rule here, if you have one item raised to a power. And so the problem is, in the example that we're looking at now, we don't have one item raised to a power. We have 2 separate items raised to powers. And so what we first need to do is we need to split this up into 2 pieces. So we can split this up into log base 5 of x cubed plus log base 5 of y to the 6th. And now each of these is in that format of just one item to a power, right? And so now we can use that third rule, which allows us to bring down our exponents. So we're using now this rule. Okay, so in this case, that would give us, bring down the 3, we would have 3 times log base 5 of x. And then this next example would be 6 times log base 5 of y. So again, I know this probably looks more complicated than what we started with, but there will be situations where you want to be able to break things down. Later on in the video, we'll also do examples where we kind of go backwards. So there are situations where you want things to be written in this kind of more compact way. There's other situations where you want to write it in a more expanded way. It's kind of like factoring, right? Sometimes you want to factor something, sometimes you want to leave it multiplied out. It really depends on what you're doing. Okay, so next example. And I would encourage you, by the way, now that we've done a few, to start to try some of these yourself. Although I would say that most of these are going to get kind of harder as we go. All right, so next one we have is ln of a times b divided by the square root of c. So there's a lot going on in this one, right? We have multiplication, we have division, we also have a square root, which can be written as a 1/2 power. So that's an important thing to recognize, is that whenever you're taking a root of a number, you can rewrite that as an exponent, which will allow us to use that exponent rule to bring down that exponent. But what do we want to do first here? So we want to kind of look at this and think like, big picture, what's going on here? We see multiplication, we see division, we see a square root. What's kind of the outermost thing that's happening? Well, the outermost thing that's happening is division, right? Because we have multiplication happening, but that multiplication is happening just in the numerator. And we have a square root happening, but that's just happening in the denominator. So big picture, we have division. So the first thing we want to do is split this up using the division to subtraction rule. And so that means that we can rewrite this as ln of a times b minus ln of the square root of c. And so now each of these pieces is kind of, we can access what we need in order to use the next rule, right? So this next one, or this first one, we can split this up with addition now, right? We can rewrite this as ln of A plus ln of B. And then how can we work with this ln of square root of C? Well, remember that square root of C can be written as C to the 1/2. And so we can take that 1/2 and bring it down using that exponent rule. And so this would be our final answer. This is as much as we can break this down into its simplest pieces. Okay, so next up, we're going to do log base 3 of 1 over 9y squared. Okay, so how does this one go? Well, again, we have multiple things going on, right? We have division, we have multiplication, we have y being raised to a power, but the outermost thing that's happening here is division. We can't access the multiplication until we get that denominator by itself. And so the first step we want to do is split this up as log base 3 of 1 minus log base 3 of 9y squared. Now, log base 3 of 1 can be simplified, but let's get there a little bit later. So generally, if you have a logarithm of just a number, in some cases you'll be able to simplify that. But let's continue to work with this second part, and then we'll come back at the end and simplify log base 3 of 1. Okay, so this can now be split up using the multiplication to addition rule, right? Because this is 9 times y squared. And so we have to be really careful here. Whenever you're subtracting, right, here we're subtracting this logarithm. If we're going to break this up using addition, we need to put parentheses around it. So this, I would say, is the most common mistake that I see students make in this section. So pay attention. Why am I putting parentheses? Well, because when you're subtracting, you're supposed to subtract that entire quantity, right? We're trying to subtract this whole thing. And so what we're doing here is we're splitting up the thing I circled in green into 2 pieces, and we need to ensure that we're subtracting that whole thing. If we did not put the parentheses, we would only be subtracting part of it, not the whole thing. Okay, so now we have, let's distribute that negative sign. So we have log base 3 of 1 minus log base 3 of 9 minus log base 3, sorry, I dropped 3, of y squared. Okay, so what else can we do here? Well, we can simplify, like we said, this and this, but let's finish with breaking things down first. So log base 3 of y squared, well, we can use the exponent rule on that, right? So we can break that down into 2 times log base 3 of y. Okay, so now we can deal with these numbers, right? So what is log base 3 of 1? Well, that's asking what power we have to raise 3 to get 1, and the answer is 0, right? And actually a logarithm of any number, a logarithm of, with any base of 1 is always going to be 0. Next, we have the power to raise 3 to get 9, and that's 2. And then we have 2 times log base 3 of y. That's not going to be able to be simplified, right? Because there's a y and not a number. So we can rewrite this as negative 2 minus 2 times log base 3 of y. So my main advice with these would be to really take it step by step. I think it's tempting to try to do multiple steps at once, but the more you try to do multiple steps at once, the more likely you are to make some kind of a mistake in terms of, applying these rules in the right order and, putting parentheses in the right place, things like that. I want to do one more example. So let's say that now we're trying to simplify log base 2 of 8 plus x times y. So let's go back and look at our rules and see if any of our rules apply to something like this, right? So the 3 rules we have are that if you're taking a logarithm of a product, you can break it up into addition. If you're taking a logarithm of a quotient, or sorry, did I say division? I meant to say addition. If you have a logarithm of a product, you can break it up as addition. If you have a logarithm of a quotient, you can break it up as subtraction. And if you have a logarithm of one item raised to a power, you can bring that power down. We do not have any rules that tell us about taking a logarithm of a sum and breaking it up. So this is not equal to log base 2 of 8 plus log base 2 of x times y. It does not work like that. I'll put a little warning symbol because this is a very common mistake to make. So why doesn't it work like that? Well, we know that when you break something up with addition, that would be if the stuff on the inside was multiplied, right? So what I have written here right now, that would be the same as log base 2 of 8 times x times y, right? And so how could 8 plus x times y and 8 times x plus y, x times y be the same, right? They're not the same. And so this is not correct. So this one actually cannot be broken down. It's a little frustrating, right? Because you look at it and you see that 8 and you're like, well, log base 2 of 8 is 3. And you see that x times y and you're like, oh, I should be able to break that apart. But this cannot be expanded. It cannot be expanded because the stuff inside the logarithm is not itself a product, a quotient, or an item raised to a power, right? Instead, it's two things being added together, and we just don't have a rule for that. So I want to look at one more example that is going to maybe initially look really similar to this last example, but we'll see that there's a key difference. So let's say that instead now we had log base 2 of 8 times 1 plus xy. Okay, so what's different about this one? Well, notice that in the last one, it was just something plus something else. This one is actually a product, right? It's a product of 8 times 1 plus xy. So there is addition going on here, but the important thing is that on the outermost level, we have multiplication, right? We have 8 times this. Whereas this one, if you read this out loud, you cannot read this as something times something, right? You can read it as 8 plus x times y, but the times comes later. Whereas this one is 8 times 1 plus x times y. So the multiplication is kind of the outermost thing that's happening in this function. Okay, so what does this tell us? Well, this tells us that we can break this down using the multiplication to addition rule. So we can rewrite this as log base 2 of 8 plus log base 2 of 1 plus xy. And then log base 2 of 8, well, that's equal to 3. And then what's the deal with log base 2 of 1 plus x times y? Well, that's pretty much the same situation we had up here, right? So this part here cannot be expanded because now we're back in that same situation of having a sum rather than a product or a quotient or a power. And so this would be our final answer. And by the way, these two expressions are not actually equal to each other, right? So if you distributed this 8, you would get 8 plus 8 times xy, not 8 times xy. 8 plus xy. So if this original one had been 8 plus 8 times xy, well, then you could have factored out the 8 and done the same thing we did down here, but it wasn't, right? It was just 8 plus xy. Okay, so I want to do a few more examples. So these next examples we're going to do are going to kind of go the other way. So instead of using the rules to start with something that is kind of all together and then break it apart, we're going to start with something that's broken apart and we're going to put it back together. So first example I want to do, so we're going to use log So to combine and simplify the following, we'll see that some of them can be simplified and some cannot. Okay, so first example I want to look at is 1/2 times log base 2 of x minus 3 times log base 2 of y. Okay, so what are we doing here? We're basically, again, just using those same rules from that we were using on the previous page, but in reverse. So let's start with this expression here. So we see that we have multiplication happening in front of the logarithm, right? And so that tells us that we can take that exponent, or we can take this number and turn it into an exponent on the x. So we can rewrite this part as log base 2 of x to the 1/2. So just using that same rule, but kind of going the opposite direction. And then same thing over here, right? We can rewrite this instead of as 3 times log base 2 of y, we can rewrite it as log base 2 of y cubed. Okay, so now what? Well, now we're subtracting two logarithms. They have the same base, and so we can put them together using division, right? So log base 2 of this thing minus log base 2 of this other thing is the same thing as log base 2 of x to the 1/2 over y cubed. And then the last thing we can do is, it's a little bit nicer, instead of writing this as x to the 1/2, let's rewrite it as the square root of x. And so this would be our final answer. Okay, so the next few examples we're going to do are going to be a little bit different. These are actually going to be ones where our final answer is just going to be a number. So I think these are kind of interesting, because we start with something that looks like it wouldn't be able to be evaluated by hand, but we'll end up with something that, that can easily be evaluated by hand. Okay, so we're doing log base 4 of 2 plus log base 4 of 32. So if you're trying to evaluate this by hand, this one could be done, right? Like this first part would be, what power do you have to raise 4 to get 2? The answer would be 1/2, right? Because 2 is the square root of 4. And then this one, there is some kind of a power that you could find that you could raise 4 to get 32, but it's going to be some kind of funky fraction that you're probably not going to be able to come up with right away, right? Because 4 squared is 16, 4 cubed is 64, that doesn't give you 32. So it's going to be some kind of a fraction. So rather than try to evaluate these each by themselves, what we can do is we can use logarithm rules to combine them, right? So if we have log base 4 of 2 plus log base 4 of 32, that can be rewritten as log base 4 of 2 times 32. And so what is 2 times 32? Well, that's 64. And so log base 4 of 64 is asking us what power we have to raise 4 to get 64, and the answer is 3. So you might not have guessed that based on our original two pieces, but once you combine them together, you're able to see that that is the answer. Okay, next up we have log base 2 of 80 minus log base 2 of 5. So I think this one is actually even more interesting, because in this case, you really can't come up with a nice number to raise 2 to get either of these, right? What power do you raise 2 to get 80? Can't come up with that. And then especially this one, there's no nice number you could raise 2 to get 5, right? 5 is an odd number. So you might not expect that we're going to get a nice clean answer here, because these just seem like each individually would be kind of a weird number. But let's see what happens when we use these, when we use logarithm rules to combine these, right? So what's a way of combining these? Well, we could use the division subtraction rule. So we could rewrite this as log base 2 of 80 over 5. So what is 80 divided by 5? Well, it's 16. You might not know that off the top of your head, but the way that I remember it is that I know that 5 times 8 is 40. And so 5 times 16 is twice 40, which is 80. So 80 over 5 is 16. And then log base 2 of 16, well, that is going to be a nice number, right? Because 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16. So our answer is 4. So again, I probably would not have expected that based on our original two pieces, but when we combine them the right way, we can see that the answer is actually 4. And by the way, I would encourage you, if you were to try to evaluate each of these separately, so not every calculator can do this. We'll actually talk more about this in the next video, but Desmos I know can. So if you go to Desmos and you type in log base 2 of 80 and log base 2 of 5, you'll see that they're both going to be kind of weird numbers, but when you subtract them, you'll get 4. Okay, so one more example along these lines. So let's do log base 5 of 25 to the 10th power. So 25 to the 10th power is a huge number, right? You would not want to have to evaluate this by hand. You would not want to try to figure out what 25 to the 10th power is. Luckily, we don't have to do that because we can use logarithm rules. So this one, we can bring down the 10. So I guess this one actually is kind of a little bit more like the other ones. We're not really, we're expanding it, but it's kind of similar to the last two. So we have 10 times log base 5 of 25. And so what is log base 5 of 25? Well, that is 2, right? Because 5 squared is 25. And so we have 10 times 2. And so our final answer is 20. So basically, as we've seen now, these rules can be used both kind of algebraically to rewrite expressions in different ways, but they can also be used to help us actually evaluate logarithms. So one last little thing in this video I want to talk about is just a couple of kind of special examples that are going to come up a good amount in calculus, and they're just kind of good ones to know. So first one is going to be something that we've actually already basically done. But let's try to simplify ln of e to the 5x minus 2. So what rule might we be able to use here? Well, in this case, we have a logarithm of a number raised to a power, right? And so we know that when we have an exponent, we're allowed to bring down that exponent and multiply with it instead. So we can rewrite this as 5x minus 2 with parentheses times ln of e, right? Just bringing that exponent down. And then what is ln of e? Well, ln of e is asking us what power we have to raise e to get e, which is 1, right? So we have 5x minus 2 multiplied with 1. And so that is just equal to 5x minus 2. So something that will be useful to be able to recognize in general is that in general, anytime you have an expression of the form ln of e to anything. So I'm just putting a star here because that star could be a super complicated algebraic expression. You know, in this example, we did 5x minus 2. It could be anything. It's always going to simplify to whatever that exponent is. So I'll say for any expression, so regardless of how complicated that exponent is, if you're doing ln of e to something, that's always going to reduce to just being that exponent. And it's just because of this logarithm rule with exponents that happens. All right, one more. So this one's a little bit different. So in this case, we're going to simplify e to the ln of x. So this one's a little bit trickier, and it's a little hard to explain it in words. It just kind of gets confusing, but bear with me. So if we have e to the ln of x, so let's think about what ln of x means. How would you describe to someone what ln of x is asking you to do with a number x? Well, it's asking you what exponent you need to raise e to get x, right? Forget about this e for a second, like cover it up. Focus just on the ln of x part. So ln of x on its own is always asking you what power you have to raise e to get x. Right? So I would pause the video if you don't quite get that and think about it. This is one of those things, I'm not trying to do this as kind of a cop-out. It just really is one of those things that it's going to sound confusing if I just keep repeating it at you. You need to really pause and make sure that you understand it. So anytime you're taking a logarithm, you're always looking for an exponent, right? You're always looking for what exponent you need to raise something to get a number. So in this case, if it's ln, it's asking you what power you need to raise e to get x, because that's the base of ln. Okay, so what is going on here? Well, we're taking e, now kind of returning to the big picture, we're taking e and we're raising it to the power that we need to raise e to get x. So what should that simplify to? If we're taking e and we're raising e to the power that you need to raise e to get x, what should that give you? Well, that just gives you x, right? Again, I would really pause it and just make sure you understand this. I know it's a little confusing, but it's basically by design, right? If we're taking e and we're raising it to the power that we're specifically supposed to raise e to get x, of course our answer is going to be x, right? Because that's the exponent we're raising it to. We're raising it to the exponent that is going to give us x. So a good kind of general rule to know that's similar to the one above is that anytime you're taking e and raising it to ln of anything, that could be any kind of weird, funky expression, it could be a number, it could be whatever, that is always going to simplify to whatever that expression is. And by the way, these two rules that I wrote down, these are also true for other logarithms, as long as the base and the base of the logarithm and the base of the exponent match. But they just come up a lot with e, and so that's why an ln, and that's why I wanted to say them with e and ln. So the way you can kind of think of it is that the ln and the e kind of cancel each other out, right? Because they're kind of doing opposite operations of each other. But yeah, these facts are just kind of handy to be aware of. All right, that is it for this video. I know this video was not the most interesting because it was just a lot of algebra, but like I said, these are just skills that are going to be really useful to have in future math classes. All right, I'll see you all in our next video.